Hello all. Today we will be learning block diagram reduction techniques, block diagram reduction rules that are required in control system to reduce a complex block diagram to a simplest form to analyze a control system. We will be seeing all the block diagram rules. So let's start. So first we'll see uh, what is a block diagram is, what is a transfer function is. So any complex control system having many elements, and these elements are used to represent various parts of a control system. It is very difficult to analyze various factors associated with the system. So block diagram reduction rules are useful to reduce such complex block diagrams to the simplest form so that the control system can be analyzed. One of the approach to do this is the transfer function approach for the system analysis. So first of all, let us know what do we mean by a transfer function is. So transfer function is the ratio of Laplace transform of output of any system to the Laplace transform of input of the system. So the transfer function is given here as g of s. S is the Laplace transform representation. G is the system transfer function. So how the input is normally represented as R, its Laplace transform is represented by R of S. So how the input is transferred to the output, that is output is represented here by C, and in the Laplace transform it is C of S. So how the input is transferred to the output is known as the transfer function of the system with all the initial conditions of the system considering as 0. So this is what the transfer function approach. So every time whenever you are finding a complex control system, you will be trying to find out how the output is changing, okay, with the functioning of the system. So all the processes are done on the input and then you are going to get the output. So this is what you are transferring the input as per the system function to the output. For example, to a calculator, if you are giving 1 plus 2, so you are giving the operation as plus. So your calculator is doing the addition operation on the two numbers and you will get 3 as the output. Similarly, will all the other functions, such a way there are many functions are there in the control system. So transfer function approach, wherever you are solving the block schematic of a system, you will try to find out the transfer function of the system. And the block diagram reduction rules are helping to make the transfer function with an edge to calculate at the output so that the system can be analyzed. What are the advantages of this transfer function approach is, first, it provides a simple mathematical algebraic equation. Second, directly gives the poles and zeros of the system. The stability of the system and output of the system for any input can be directly determined from the poles and zeros of the system. So this is very advantageous. Whenever you are finding out the transfer function of the system, you will come to know what is the output. From that output you can predict the input also, and from the transfer function you will come to know what are the poles and zeros which are responsible or which will help you to find out the system stability and another analyzing parameters of the control system. That is the advantages of transfer function approach. Now let us see what is the definition of a block diagram. So the simplest form of the block diagram is a single block which is having one input, one output. The interior part of the rectangle. Normally the block diagram is represented by a rectangle and the function of the system is represented inside the rectangular block. For example, this is a rectangle which is representing a system, and its function here it is given by ddt. Okay, this function can be anything based on the system. Okay. What is the input? It is given by the inward arrow. This is output given by the outward arrow. So this x as the input, y as the output. This is the normal terminology used for representation of the system, input and output. So what is a block diagram is? It is a pictorial representation of the cause and effect relationship of a system. So block diagram is a shorthand graphical representation of a physical system which illustrates the functional relationship among its components. Simplest example of it, we can take the making of a coffee. Okay. So what are the ingredients that are required to make the coffee? Normally we are taking at 3. Okay. So first is milk, which may be hot or cold based on your requirements. If you want to have a cold coffee, you will take a cold milk. Okay. And hot, so you are going to take in hot milk. Then a coffee powder and a sugar. So based on your requirement, you will select all the quantities, that are the proportions will be decided by the user. These proportions you can mention here. Let's say you are taking half teaspoon of the coffee, you are taking, let's say, half teaspoon of the sugar, and you are taking 1 cup of the milk. So this will multiply to this will multiply to this will multiply to this. Now all these three are added together, which is indicated by this summation sign, and then you will get the coffee. Now here this is an input arrow, this is input arrow, this is input arrow. So for this system of making a coffee, you are going to require 3 inputs. When you are adding all these 3, you are going to get your output, that is a coffee. Now there are 2 methods of making the coffee. First is manual and second is a vending machine, that is a coffee vending machine. So all these 3 either together blended by a system or they will be blended by an hand. So either a manual or a coffee vending machine. So what are the processes that are involved in the coffee vending machine, that will be shown by the block diagram. So either you are using these two. So this is the simplest example of the block schematic that are used to represent making of the coffee. Now what are the components of a block diagram? Let us see that. System components are also known as the elements of the system. Elements of the block diagram used to represent a particular system. So block diagram has 4 components. First, signals. Second, system or block. Third is summing junction or summing point. Fourth is pick-off or take-off point. So these are the 4 main elements of a block diagram in control system, and these elements are used to show any complex block diagram in control system. Now let us see the representation, pictorial representation of all these elements. So first is your R of S is the input given by the inward arrow. C of is the normal terminology that is used to show the output of a system. R of S and C of S. Arrowhead indicates either whether it is an input or it is an output. So these are the signals that are used in control system to represent the block diagram connectivity. Next is input as R of S, output as C of S, and there is a system which is shown by a rectangular whose function gain is shown inside the system rectangle called as G of S. So this is the representation of a system. Third is if you are having R of S, which is given to 1.1 system. Same R of S you can give back as an input to the system again. So this is, you can call it as good as a feedback. So this is R of S. This point is called as the takeoff point. You are taking the input again to the another point, that is a takeoff point. Next is the summing point. When there are multiple inputs, like we are seeing in the coffee vending machine, there are 3 inputs. They are added together and then you are going to get the coffee as the output. So here we are going to use the summing point, which is indicated by a circle with a cross inside that. So R1 of N, R2 of S and R3 of S. These are the three inputs. R is the always terminology used in control system to represent the input, and the signs here can change. This can be plus, 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 this can be plus, plus, minus, 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 plus, anything can be there. Based on that sign, the output will be generated as C of S is equal to R1 of S plus R2 of S minus R3 of S. This is the third summing point that is used for representation of multiple inputs given to the addition or subtraction for a system. Next is the pick-off point. It is also called as the takeoff point, where one input, single input is given at multiple input to systems or inputs, or the other way. So this is R of S is given at multiple inputs to the systems also, or to the blocks, or to another inputs, or to summing points or takeoff point. So this is called as the pick-off point. So T is called as the takeoff point, P is called as the pick-off point. You can use this convention with your convenience also, but normally these are the conventions that are used. Now the operations of addition and subtraction have special representation. The block becomes small circle called as a summing point with the appropriate plus or minus sign associated with the arrow entering the circle. Any number of inputs can be entered in a summing point. The output is the algebraic sum of inputs. Some books use a cross sign in the circle, or some also use a simple plus sign inside the circle. This is also used here, okay, instead of a cross sign. So this is X of S, R of S, Z of S equal to X of S plus R of S, X of S plus R of S. Here one sign is minus, so X of S minus R of S. So it can be written like this also. So inside this there is a plus sign which is written like this also. So there are some books which are representing this also. So you can use any one, but the normal practice of representing it by using a cross sign. Okay. So this is X of S given as input, R of S another input, U of S another input, plus minus. So this will be X of S minus R of S plus U of S. This is the output. So there are n number of inputs for the takeoff for the summing point only. Now let us start with the block diagram reduction techniques or rules. First, when you are having more than one block connected in cascade, there are many blocks that can be connected in cascade, and all of you know cascading means output of one block is connected to the input of the next block. Cascade means in series. So multiplication of all the individual transfer function is nothing but the output of this block schematic. So let's say how it can be represented. So this is first system G1 of S, whose input is R of S, output is C1 of S. This output C1 of S is connected to another block, that is G2 of S, whose output is C2 of S. Then the third block is there, whose function is given inside, that is G3 of S, whose output is C of S. So we can say that output of one block is connected to the input of next block, output of second block is connected to input of third block, and so on. So there can be n number of blocks. So here it can be Gn of S. There can be n number of such block connected in cascade. So what is your G1 of S? It is C1 of S into upon R of S. G2 of S is C2 of S upon C1 of S. G3 of S is C of S upon C2 of S. So output will be here. If you multiply all these three, then this will remain as G1 of S into G2 of S into G3 of S. So this will get cancelled out here. This will get cancelled out here if you multiply it. So your total R of S upon G of S, that is output upon input, that is U of S upon R of S, here it will be given as, this is nothing but what, multiplication of all these three, G1 of S, G2 of S and G3 of S. So this will give you output C of S upon R of S if we multiply all these three together. So this is the transfer function of the system where the blocks are connected in cascade. So R of S is input, C of S is output. So the combined transfer function is G1 of S into G2 of S into G3 of S. Now rule number 2 is when the blocks are connected in parallel. Okay, so one input is there which is given to three different systems, G1 of S, G2 of S and G3 of S. These systems can be n number. So here there can be n number of such systems where this same input will be given. So this can be n number of such systems. For example, here only three systems are represented. Output of these systems will be C1 of S, C2 of S and C3 of S, and this is added with the summing block plus plus and plus. So the output here will be C1 of S plus C2 of S plus C3 of S. But what is C1 of S? What is C2 of S and what is C3 of S? So for that we need to find out the transfer function for each. Okay. So equivalent block diagram for this will be G1 of S plus G2 of S plus G3 of S, that is C of S as the output. So here C of S upon R of S is equal to G1 of S plus G2 of S plus G3 of S. So if you find out your G1 of S, okay, it will be C1 of S upon R of S, C2 of S upon R of S, C3 of S upon R of S. So combined R of S will be there. Okay, so you are going to get here G1 of S plus G2 of S plus G3 of S. So this is what the transfer function of the system, which is G1 of S plus G2 of S plus G3 of S. It is same as that of the parallel connection in any system we are using. So this is the transfer function and the equivalent block representation of the blocks when they are connected in parallel. Third rule is changing the position of the summing point with each other. Means if we are having two summing points in the system, then how we can change their positions. So first let's see, we are having R of S as input 1, input 2 as X of S, and it is given to a summing point with a plus sign, plus plus. So what will be your output here? R of S plus X of S. Now there is another summing point. So output of the first summing point is given to the input of second summing point with a negative input, that is minus Y of S. So what will be the output here? R of S plus X of S minus Y of S. Now let us say if you want to interchange these two summing points, here this and here it will be this. Okay. So R of S is input 1 as it is. So we will change the summing point here. So I will take Y of S here with a minus sign. So I have taken this summing point here, this summing point here. So what will be my output here? R of S minus Y of S. Now my second summing point will be coming here. So input 2 will be X of S. So it is changing. So with the change in sign also I have taken this summing point here. So what will be the output? It will be R of S minus Y of S plus X of S. So interchanging the summing point is quite an easier task. So what we have done? We have changed the input, another input X of S and Y of S. So that we will get the same output in both the cases, though we are interchanging the summing point also. Now rule number 4 is when we want to shift a summing point from a position before a block to the position which is after a block. Means we are having two elements in the block diagram, a summing point and a system block. So let's say you are having this summing point, plus minus is the sign, R of S is input 1, input 2 is X of S. Output of this summing point is given to a system whose function is written inside this rectangular block, which is G of S. So what will be the output here? Output is R of S plus minus X of S multiplied here by G of S. So this will be R of S into G of S plus minus X of S into G of S. Now what we want to do here is, this is the summing point at point A. We want to shift this summing point after this block at this point B. What we want to do here? We want to change the summing point from point A to B. So we want this summing point should be after this block, provided that our output should remain same. Let us see how we can do this. So first, we want to shift from A to B. So let us draw R of S as the input is going to remain as it is not going to change. So this R of S will be given to the system G of S, and we want the summing point should be after this block. So R of S will be as it is. What will be the output here? It will be R of S into G of S, correct? So what is? This is point number A, where our summing point was there. We want the summing point should be shifted after the block at point B. So I had taken the summing point after the block. What will be changed in the input? What we want? Here input is R of S into G of S. So R of S into G of S is there. So this is fine. What are the next input we are going to need? It is X of S into G of S. What is the input to this summing point? It is X of S. So there is no multiplying factor G of S. So we need to multiply the system gain G of S to this input X of S. The signs will remain same, plus minus. So this is what we are going to do, multiply it by G of S and then provide another input X of S to the summing point with the same sign as plus, minus and plus. So the summing point at point A is shifted to point B, and so your output will be C of S is equal to R of S into G of S plus minus G of S into X of S is remaining the same, though we are changing the position of the summing point. So it is shifted from point number A to point B. Now rule number 5 is shifting a summing point from a position after a block to a position before a block. Okay, so we are going to do the reverse of the previous case. R of S is the input which is given to your system having a function G of S. So its output is R of S into G of S. And here we are having the summing point which is after this system block. This output of the system is given as input to the summing point which is R of S into G of S. And another input is X of S with a sign plus minus. So what is the output here then? C of S is R of S into G of S plus minus X of S. Now what we want to do? This is the summing point after system block, and we want to shift this summing point before the block at point A. So this is what we want to do. Let us see how we can do that. So first we will draw the system, that is G of S, with input and output. What is the expected output here? Same. C of S is G of S into R of S plus minus X of S. And now this is R of S. Input is going to remain same. This block we are shifted here. We want the summing point should be at this point. Now it is shifted to point number A. R of S is the input. Next input here is what? X of S. So this is multiplied by 1 upon G of S, and then the input X of S is given to you with the same sign as plus minus. So what will be the output of the summing sign here? This will be R of S plus minus X of S into 1 upon G of S. And this complete component of the summing point will be given as input to G of S. So output of the system here you are going to get is G of S into R of S plus minus X of S into 1 upon G of S. So G of S into R of S will come here, plus minus sign G of S into X of S into 1 upon G of S. So this G of S will get cancelled and you are going to get only X of S. So this is what we need to do the arrangements whenever you are shifting the summing point from point number B to point number A, and this is what we are going to get the same output in both the cases, though we are shifted or we are interchanged the position of the summing point and the system block. So this is what. The next is shifting a takeoff point position before a block to a position after the block. So same whatever we are done with the summing point and the system block, we are going to now learn in case of the takeoff point. So first the takeoff point is after the block. So this is the system function g of s indicated by a rectangular block with the input r of s here. Output is c of s is equal to r of s into g of s. This is the takeoff point, that is A. So here you are going to get c of s is equal to r of s. So this will be r of s only. Correct? Now this takeoff point is before a block. We want this takeoff point should be shifted at B after a block. Let us see how we can do this. So this c of s is equal to r of s. So r of s is the input, will be given directly to the system because we want to shift this takeoff point after this block. So this is c of s equal to r of s into g of s. We are getting it as it is. Now this takeoff point at point A, we have taken it at point B. So it will be multiplied by 1 upon g of s, because at this point also this output is same, c of s, r of s into g of s, but we want that here it should be only r of s is equal to c of s. So we will be multiplying this with 1 upon g of s. So this g of s will get cancelled and you are going to get c of s is equal to only r of s. So this g of s will get cancelled here. Correct? So this will be having c of s is equal to r of s. So whenever you are shifting a takeoff point which is before a block to a point after the block, you need to multiply it with the reciprocal of the current gain of the system. So this is what point A, we have shifted it to point B. Okay. Next is shifting a takeoff point from a position after a block. Now the takeoff point is after a block and we want to shift it to a point before the block. Let us see the condition. This is r of s as the input. Now we are having the takeoff point which is after this block. So we are having both the output of the takeoff point and output of the system are same. C of s is equal to g of s into r of s. Here also c of s is equal to g of s into r of s. This is the output. This is the takeoff point which is after the block. We want that this takeoff point should be shifted before the block at A. This is indicated by the arrow. So let us draw the takeoff point before the block. At what parameters needs to be changed. So this is the g of s as it is. We are going to get the output as c of s equal to input into the system function r of s into g of s. This is at point B. We want to shift it to point A before the block. Let us draw this. So we have drawn this as r of s. This is what takeoff point. So here I am going to get r of s. What we want here? It should be r of s into g of s. So what we'll do? We'll multiply with the current gain of the system. This is again what? Another multiplier we are adding. So this is c of s is equal to g of s into r of s, which is the expected output when the takeoff point after a system block is shifted to a point before the system block. So this is what? Shifting of the takeoff point. Now next is shifting the takeoff point to a position before the summing point. Here we will be learning shifting of or interchanging of the summing and the takeoff point. So first we'll consider the case when the takeoff point is before a summing point. So first we will be having the summing point. This is r of s as another input, x of s is another input. So output of this is r of s plus minus x of s, and the takeoff point is before the summing point. So this is what our takeoff point. So here you will be having r of s as the output. We want this takeoff point should be shifted after the summing point to the point B. So this is C of s is equal to R of s. C of s is equal to R of s plus minus x of s. This should remain same. Now, first, as we want to shift the takeoff point after the summing point, we'll draw the summing point first. This is R of s and x of s. Points, summing symbols are going to remain same. Plus, plus minus. Then, what is the output here? C of s is equal to R of s plus minus x of s. It is as it is. Now, takeoff point is shifted to point P. So, from point A to point P. Let us draw the takeoff point. What I want here, the output is only R of s. But what I am getting here? R of s plus minus x of s. So, I need to remove this x of s term. So, if it is added here with plus minus sign, I will do here minus plus. So, here it will be minus plus with an x of s sign. This is plus. So, at the output, what we are getting? R of s plus minus x of s minus plus x of s. So, this will get cancelled out, and here your output will be R of s. So, this is how you are interchanging the summing point and takeoff point. So, here the takeoff point was before the summing point and we have shifted it to the after the summing point. Now, next is the reverse case when the takeoff point is position after summing point and then it is changed to a summing point's previous position. So this is your R of s. This is the summing point with another input x of s. C of s is equal to R of s plus minus x of s. Now here you are having the takeoff point after the block. Previously we were having the summing takeoff point before the block. So this is what again you are going to get C of s equal to R of s plus minus x of s. So here both the outputs are same. You are having the takeoff point after the summing point. Previously you had seen that the summing point was before the takeoff point was before the summing point. Now we want to shift this to before this. This is what we had seen, and we have done the reverse operation here and we have obtained here as the same output. Okay, so let us see how this can be done. So we have shifted this to the point before. So first draw the summing point here, R of s plus minus x of s. We are going to get the same R of s plus minus x of s. Point was at B, we want to shift it to point A. Okay. What we want here output is R of s plus minus x of s. So we are going to add x of s with the same symbol, same summing point we have to replicate here, okay, in the takeoff point. So here we are going to get C of s equal to R of s plus minus x of s. Okay. So previously we had done the reverse operation. We need to subtract x of s in order to get R of s only here at the output. So this is the output. Now eliminating a summing point in the closed loop system. Eliminating a takeoff and summing point in the closed loop system. So if we are having R of s as the input, okay, and this is applied to a summing point, output of this is U of s given to U of s at the summing at the input to the system. C of s, this is H of s and B of s. Now this is called as the feedback loop. This is called as the summing point. This is the error signal and this is the feedback signal that you are getting. This is the output of the system. We want to represent using only one block schematic, removing the feedback loop and the summing point and the takeoff point. Now this contains the feedback, this contains a takeoff point, and this also contains a summing point. We want to represent this using only a single block. How it can be shown? So here it is represented as R of s as the input, C of s as the output, and the transfer function of the system is G of s upon 1 plus minus G of s into H of s. These symbols will change based on the symbols given in the system. So normally this is G of s 1 minus plus G of s into H of f. If it is plus minus, if it is minus plus, it will be plus minus G of s into h of s. So this is how eliminating a summing point in the closed loop system, which is having a takeoff point and summing point. This b of s is the feedback signal which is getting from this takeoff point, which is part of the output, and this error signal is the difference of this r of s and the b of s. So total, this is the complete representation of the feedback loop using only one block. So all the complex control system using all these block diagram reduction rules, we will try to get only in this format so that it will be analyzed and used for system analysis purpose. Thank you. So this covers the block diagram reduction rules used in the control system, and these rules will be useful for reducing the complex control system block diagram to the simplest form as we had seen it in the last slide, that is rule number 11. From that we can analyze the poles and zeros of the system, which can be used to comment on the system stability. So next module will cover the block diagram reduction rules application in actual the block diagrams of a control system. Thank you.